Alright, so in metallurgical joining, there are ways that we join two or more metals. It could be the same metal or different metal. So this could be, let's say, this one part, this another part, and these are the two parts that we want to join. They could be the same metal or different metal, right? One thing we do is that we have the metal, right? So let's say the metal that we are trying to join, which is this one and two, that's what we call the base metal or the parent metal. And then most of the times when we join this metal, we use them for engineering applications. And then one thing we do is that we ensure that it doesn't fail at the place where we do the joining, right? So we make sure that the material we use in the joining is actually stronger than the parent metal. So the material that we use is what we call the filler metal, right? Filler metal. And then because we want to ensure that even if after the joining, if the component is to fail, it doesn't fail at where we join, right? Yeah. So what we do is that, as I was saying, we use a metal that's of a higher strength or higher properties, better properties than the base metal, so that when we do the filling, it doesn't fail. But because we are doing metallurgical joining and then we are using heat, right? At times we even use pressure. We are using heat, and at times it could be both or just heat or pressure, one of them. There end up being a change in composition, right? And then the material science, one thing is that when there's a change in any of these three, right, then there's a consequent change in once there's a change in any of these three, one or more of these three, then we expect subsequent change in the properties, right? So since there's a change in heat, pressure, or composition, then we expect a change in properties, right? Properties. And once there's a change in properties, we expect a change in the performance, right? And then in this case, whenever we do joining, we are going to use the joint unit in an engineering application, and I want it to perform in a particular way. And since there's been a change in this heat, pressure, or composition, there'll be a change in the performance, which we usually want to make sure we know how it is so that it doesn't fail unexpectedly, right? So this is what happens. What we do is that the filler metal, which we call hash. So then, by the way, this joint here is basically a butt joint because we have one part, right, and we are bringing another part together and weld them at their butts, right? There's a butt joint. But then we are creating what we call a groove, right? A groove is basically we are creating, we're creating some kind of channel, right, at the joining point so that we can put in the filler metal. So this point here, so you see this side here, that looks like some sort of V. That's the groove. We are creating that side so we can put the filler metal there. The filler metal, we expect it, we ensure that it's of better properties than the base metal, right? So this is what happens. When we try to put, let's say we apply heat to this filler metal, melt, and then we try filling it to this side, right? By the welding process that we've chosen, which there are a lot of them, certain metal, right? We have plasma welding, we have laser welding. Some of them are also use only heat, some of them use heat and pressure, some of them use just pressure. There are a lot of them, right? So let's see, this is just from the top, right? Kind of like bird's eye view. This is just from the side. So the good profile is something of this sort, right? We don't want any undercut, we don't want any underfill. So this basically, and we don't want any incomplete fusion, right? So it completely fills the joint. What I just said, I just defect, forms of defect, right? So this is a good profile for weldment. And then this side that we've melted the filler metal and we've filled it here to completely fill the groove. When we form something of this sort, it's called a weld bead, right? A weld bead. Okay. One thing that could happen is that because we are applying heat, right? This metal here, we call the base metal, the 1 and 2, could kind of like get into this one here, the weld bead, right? So these ones diffuse into this one, and then they change the composition of the whole thing. Instead of it being the pure filler metal that we added, it's no longer the filler metal. It's something we call the weld metal, right, or the weld bead. So basically, the weld metal, M, right, is the sum of the base metal or the parent metal plus the filler metal, right? Yes, we are saying this because we have the filler metal, but then because we're applying heat and everything, they melt and then there's a mixture, right? So basically dilution, as we are talking about dilution, right, is a change in the composition. The change not just in the composition, the change in the chemical composition of the filler metal, right? So basically we have a filler metal, but put it here, and then the metal from the base parent metal diffuse, some of them diffuse into it and mix, and then it forms something new, right? So dilution is the change in the chemical composition of the filler metal due to admixture of the base metal in the deposited weld bead, and there's the weld bead as we're seeing, right? Okay, but there are times where because we know we call something dilution factor, depending on the welding metallurgical welding process that we are using. Each and every one of these have a welding factor depending on how the base or parent metal gets to form some sort of mixture with the filler metal to form. So each and every metallurgical joining process, especially the welding method, have their own dilution factor, right? And then the dilution factor is it just explains, it just expresses the amount of the parent metal that forms an admixture with the filler metal, right? Okay, so this typical example, we're going to use this to check the understanding, right? So let's see. What this says is that a plate, right, of composition 9% nickel, 91% iron is welded with an inconel wire. Basically, this means that this is basically what you call our parent metal, right? This is our parent metal, right? It's welded with an inconel wire, and this becomes our what? Our filler metal of composition, this and this, right? The weldment to be used in marine environment, right? Okay. And then the welding process use has a dilution factor of this. They didn't specify, they just give dilution factor. Determine whether the weldment will corrode in the marine environment. We will be able to determine whether to corrode or not depending on the element that enables in this case, the actual first metal, that helps the first metal to develop good corrosion resistance, right? Then again, if you've not done it before, you won't be able to identify the element. But in ferrous metals, the main one of the alloying element that helps the metal to develop high or good corrosion resistance is actually this nickel here. Sorry, not the nickel. It's the chromium. It's actually this chromium here. And then a lot of work has been done on this, and it shows that if the chromium weight percent is greater or equal to 13%, then it will have good corrosion resistance, right? Good corrosion resistance. But then if it is something less, then the corrosion resistance won't be good, right? So our work here is how to be able to determine whether to corrode in the marine environment we're talking about or not will depend on the amount of what's the name, the weight percent of the chromium in the weldment, right? So you're saying in the weldment, right? And if we explain that if we are to do the welding, the ones in red here, these ones here are the parent metals, right? And the filler metal is the something that we have let's say something of this sort. We bring it here and we apply heat, right? And it melts and it fills the side. And because there's some kind of dilution, the parent metal gets into the filler metal somehow. What happens is that we get a weld bead here, and the weld bead is not purely the filler metal, but an admixture of the parent metal and the filler metal, right? So we want to check if this weldment, right, or the weld metal will have a chromium percent, that is a chromium weight percent that is equal to or greater than the 13. If it is so, then it will have a good corrosion resistance. It won't corrode in the marine environment. Else, anything less and it will corrode, right? So that's what we do. I'm going to follow a step-by-step process. Basically, we list the element out. So let's see. The element weight percent. this weight percent, right? And then we have let's say base metal. Those are the parts we are trying to join: base metal, parent metal, right? And then we have the filler metal, which is we are expecting to have what's the name, better properties than the base metal. That's why we are using it. But then because of the dilution of it, the properties can get worse. So we want to see if it will actually perform well in the after it has been welded. And there's the weldment, right? So this base metal is the parent metal. This filler metal is what we are the filler metal we are using. This W is the weldment or the weld bead, right? So that's what we go. And one thing that was said in the question is this 40% here, right? You're seeing a dilution. The welding process has a dilution factor 40%. This 40% here represents the parent metal, because what did we see? We said that when we do the welding, the one that dilutes the other is actually the parent metal. So the 40% is basically for the parent metal. That's the dilution factor. So let's see. The dilution factor for the parent metal is 40%, right? This 40% is basically 0.4. This will mean that the dilution factor for the filler metal will be 100 minus the 40%. So that gives us 60%, which is basically 0.6, right? And this is what we will use, right? And then one thing we should understand is that basically because the weld metal is a mixture of the what do you call it, the base metal and the filler metal, right? Weld metal comes from the filler metal. It's a mixture of these two and the base metal. We should be able to find the percentage of the element in them. So let's write out the elements. We have nickel, we have iron, right? Nickel, and then we have iron. Let's see what else we have. We have nickel, it's written. We have chromium now. So chromium. It could be complex than this, but that's just an example for us to understand what's happening, right? Let's see. Okay. So now we know that in the base metal, the parent metal, which is the plate in this case, the nickel is 9, iron is 91, right? Nickel in the base metal is 9%, iron is what, 91%. This will mean that there's no chromium in the parent metal or the base metal, right? For the filler metal, we have nickel 20, nickel 80, chromium 20. Nickel 80%, chromium 20. This means that no iron in the filler metal. And then when you look at this, you should see clearly that the original percentages of them add up to 100. Add up to 100, this plus this gives 100, this plus this gives 100. And so that means that whatever we get at the end of the weld metal should be 100. And then we've seen the dilution factor for the parent metal, the base metal. We said that was 40. So that would mean that the amount of the iron nickel in the parent metal that gets into the weld metal is basically the 40% of the 90, which is basically 0.4 times the 9. We'll find what that means. We'll find the actual answer. Then again, for the base metal, this will be 0.4. The amount of iron in the base metal that gets the weld metal, 0.4 times the 91, right? For the filler metal, the dilution factor is 0.6. That will be 0.6 times this, 0.6, right? And then 0.6 times this, and we get this. And when we add the corresponding values for this all here, we get the nickel in the weld metal, iron in weld metal, chromium in weld metal. And with this, we can get to know the chromium there and get to predict whether it will corrode or not corrode in the marine environment. So now we did the calculations. Okay, so calculations now. Okay, so that's 0.4. We are now doing it for this one. We are doing it for everything here, right? Okay, that's 0.4 dilution factor, and the x will be the percentage, right? So when x is what, 9, that gives us 3.6%, and when x is what, 91, that gives us what, 36.4%, right? And then now we move on to this side. We are checking for here, everything here, right? That's 0.6 x when x is 80, there's 48, percent. When x is 20, and we have 12%. Right, now we can add up. We can add up this way, this and this, right? So let's see, 3.6 plus 48, 51.6%. This is just only this, so 36.4%, and then this is just this is 12%. So to not check if you're on the right power, you have to add them and see if you get 100. 51.6, 36.4, 12, and that gives us 100, right? That gives us 100. So basically, this is the composition of the whole metal. So now it is clear the amount of chromium in the world metal. So this is world metal, and this is the chromium weight percent, right? So since the chromium weight percent, let's see, chromium weight percent of the world metal is less than, it's less than 12%. This implies that the weldment will corrode in the weldment will corrode in the marine environment. Yes. So by this, we've been able to determine whether the weldment will corrode or not, right? And this is a very simple example of typical examples of scenarios that happen in natural, what do you call it, environment. In reality, yes, in reality, that's what I'm going to say, right? So this shows us that since the amount that we are getting here, sorry, this should be 13. This should be 13. Since we have 12 for the chromium amounts, for the chromium in the world metal, and since this 12 is less than the 13, the weldment, which we've identified to be this side, this one right here. Let me use a different color. We've been able to identify that this weldment here will corrode in the marine environment, right? This weldment will corrode in the marine environment. So weldment, weld bead, weld metal, they are the same. So this shows us that the weldment will corrode in marine environment. All right.